Porter, as you know. Today I'll be talking to you about the effect of age and antibiotics on the dermal microbiome. Most people don't know that that's in 2013, $75 billion was spent to address skin problems. And the cost and prevalence of this issue is increasing with time. In order to aid these people with these dermatological issues, the microbiome was studied. The microbiome is the environment where microorganisms live and grow. What I believe was that an unhealthy skin environment would be associated with variables and microbes that would support a state of microbial dysbiosis. Microbial dysbiosis is an imbalance between microbes, good and bad. It's just an imbalance. I also believe that a healthy state would be associated with a more abundant and diverse population of bacteria that would exude a symbiotic relationship. So, in order to do this, 208 samples were obtained through the American Gut Project database. These samples were extracted and underwent next generation sequencing with the 16S gene. After they were sequenced, the samples underwent analysis using the two computer programs called CHIME and After running these analyses, I found that antibiotics and age were significant variables that impacted the microbiome. So I wanted to look into these variables. Figure 1 is a alpha diversity plot, which shows the fluctuating abundance of bacteria between the two environments of people who have and have not taken antibiotics. As we can see, people who have taken antibiotics have a lower abundance of bacteria, which was expected. But what I focused on was looking at the difference between these two environments. And because we can tell that there's a difference between these two environments, I can say that antibiotics is a influential variable on the microbiome. After looking at antibiotics, I wanted to look at age. So figure 2 looks at is a taxonomic plot, and it looks at the abundance of bacteria over time. Age, categorized by age. So we can see that over time, bacterial abundance is increased until it gets to about 70 plus, which could be due to at older age they have a weakened immune system and thus have a lower abundance in bacteria. But really what this figure shows is a variable but stable environment, a microbial environment, saying which we can say that age is a significant variable. After seeing how these two variables are significant alone, I wanted to see how together they can impact the microbiome. So figure 3 is a microbial dysbiosis index. This looks at the ratio between helpful and harmful bacteria. So this looks at This looks at the two environments of people who have not and have taken antibiotics, and as a function of time, and whether these environments are healthy or not healthy. So as we can see that people who do take antibiotics, let's look in between this 40s category. People who have not taken antibiotics have a higher amount of helpful bacteria, and people who have taken antibiotics have have a higher amount of harmful bacteria. And we can see that people who have taken antibiotics have a lower abundance of bacteria, while people who have not taken antibiotics have a higher amount of bacteria, which was, we knew that. But it could suggest that people who have a lower abundance of bacteria are subjected to being in a state of microbial dysbiosis. So with this, we can say that these two variables, age and antibiotics, have a large impact or a significant impact on the microbiome. So I wanted to see what types of microbes would represent these two variables together. So figure 4 is a random forest model which looks at the types of the top 10 most significant bacteria impact the microbiome based off of the two variables. So Neisseria and Lactobacillus are two significant bacteria. These two significant bacteria, And Neisseria has strands that are associated with gonorrhea and bacterial meningitis, while lactobacillus can be found in yogurt along with other probiotics and is also known to be beneficial to the immune system. So, yeah. So, we're seeing that there is a balance between harmful and helpful bacteria within the microbiome. Seeing the balance between harmful and helpful bacteria in the microbiome, however, there is a significant shift in not only the microbial community but the bacterial hierarchy when antibiotics is introduced, which is seen in previous figures. But with all this being said, I can say that my hypothesis was supported because an unhealthy environment was associated with bacteria that was less abundant and was associated with a higher amount of harmful bacteria, while a healthy environment was associated with more abundant and more diverse bacteria, and was also associated with more helpful bacteria. So, in future studies, I plan to look at the microbiome of the scalp and the ailments that associate with alopecia, which is hair loss. But this study provides a solid foundation. Yes, solid. It's a solid foundation on the skin microbiome and the variables and microbes that impact it. Because the scalp is just a variation of, your normal skin that you find on your leg or your arm. So, yes, I hope you were educated today. Yeah, that's about it. Oh, just to go more in depth, the analyses that I ran, it was called linear model. So yeah, linear model pretty much just shows the significance of a variable and how much that variable impacts the microbiome. It gives two values, p-value and r-value. P-value just shows whether it's significant or not. If you get a value that's less than 0.05, then you have a significant variable. But if it's more than that, then it's not significant, because 0.05 is like the margin of error, and you want a low margin of error. R value just shows how much it impacts the microbiome. In this case, antibiotics, it impacted about 15.6%, but age category impacted 30.4%. So there's a big impact on those two variables. That's why I looked into them. Yes. And yeah, that was about it. That's all that kind of went into that. But yes, as I said, I hope you were educated today. Thank you all.